given the definition that we gave in the last lecture of spin as essentially an angular momentum operator algebra that doesn't actually have a obvious counterpart of particle motion, let's take a look at the operator algebra and the associated states, their eigenvalues, their eigenstates, etc., of the most basic case, the most basic non-trivial case, spin 1/2. Spin 1/2 is the system that you should think of if the quantum mechanical system you actually are trying to understand is too complicated. Spin 1/2 is about as simple as quantum mechanical systems get while still having rich behavior. So essentially what we're working with is S, which was our spin angular momentum counterpart for the L quantum number in orbital angular momentum of 1/2, which means we have an M counterpart in the spin angular momentum of either -1/2 or +1/2. So that's the structure of our system. We're working with two states. So S is 1/2, and our allowed values of M are then -1/2 and +1/2. The two states that we're working with then, I'm going to call them chi plus and chi minus. And what that means is that we're working with S is 1/2 and M is either +1/2 or -1/2. Another very common notation, and one that I'm going to use in this lecture, is to call the plus case up arrow and the minus case down arrow. So spin up and spin down. What's nice about this, the fact that we're working with a two-state system, is that no matter what our operator is, it's going to have a representation as a 2x2 matrix. The vectors that we're working with then, this chi plus, expressed in this basis, the basis of spin up and spin down, our chi plus vector, which I'm also writing as just up, is given by simply 1, 0. Likewise, chi minus, or spin down, is given by 0, 1. If these are the vectors that we're working with, what are the operators that we're working with? Our operators are going to be things that act on these two component vectors, so they're going to be 2x2 matrices. For instance, let's consider S squared. We know what S squared does from our consideration of the operator algebra. S squared, which is our counterpart for L squared, S squared, acting on the spin up case, is going to give us our eigenvalue, which was h bar squared s plus 1, and this is an eigenstate of S squared by construction. S, in this case, is 1/2, and if you plug this in, you find out this is equal to 3/4 h bar squared. We can use this sort of expression, which of course has a counterpart, S squared, acting on spin down. The spin down state is also an eigenstate of S squared, with the same eigenvalue, 3/4 h bar squared. I'm having trouble with my fractions today. 3/4 h bar squared spin down. These two, we can write those out in the matrix notation. Not knowing what the operator S squared looks like, let's just write it as A, B, C, D, four unknown components in our vector. Spin up, we know what that looks like. That's 1, 0. And that's going to give us 3/4 h bar squared times our spin up, 1, 0. Likewise, we have our action of S squared on spin down, which we know about. Our unknown A, B, C, D matrix acting on 0, 1 gives us the same thing, 3/4 h bar squared, 0, 1. Now each of these we can expand out. We can do the matrix vector product here, and when we do, we get AC is equal to 3/4 h bar squared, 1, 0. Likewise here, we get BD is 3/4 h bar squared, 0, 1. This tells us that A is equal to 3/4 h bar squared, and that C is equal to 0. And this tells us correspondingly that B is equal to 0, and D is equal to 3/4 h bar squared. What that means is that our S squared operator expressed in this basis is 3/4 h bar squared, 0, 0, 3/4 h bar squared. It's more conventional to factor this 3/4 h bar squared out front and just write this as 1, 0, 0, 1. the identity matrix, essentially. So this is our matrix representation of S squared. What other operators do we have to work with? The next one to consider is the other one where we have easy eigenvalues, S sub z. We know what S sub z does. Similarly, S sub z acting on our spin up ket gives us h bar over 2, our positive eigenvalue, times our upwards ket. Spin up ket. S sub z acting on spin down gives us minus h bar over 2 times our down ket. Similarly to the last slide, we can write out matrix representations of this. So some unknown A, B, C, D, and these are now different A, B, C, D from the last slide, acting on 1, 0 gives us h bar over 2, 1, 0, or A, B, C, D. Now these A, B, C, Ds are the same as these A, B, C, Ds, since we're considering the same operator. Acting on 0, 1 gives us minus h bar over 2, 0, 1. As before, you can do these matrix vector products and get AC is equal to h bar over 2, 1, 0, or B, not over, just BD in a column vector is equal to minus h bar over 2, 0, 1. Same sort of results? Fine. You find the same sort of results. A is h bar over 2, C is 0, B is 0, and D is minus h bar over 2. Which means we can write down our matrix expression for S sub z in this basis as simply h bar over 2 times 1, 0, 0, minus 1 for A, B, C, and D. So this is our expression for S sub z. We have S squared, we have S sub z. What about S sub x and S sub y, the other things that we might hope to one day observe, the spin angular momentum x component or y component? Unfortunately, S sub x and S sub y are not terribly easy to evaluate on their own. So our starting point here is going to be S plus and S minus, the spin angular momentum equivalent of the raising and lowering operators. You can probably guess what sorts of equations we're going to use to determine S plus and S minus here. For instance, S plus, acting on the down state, gives us something proportional to the up state. I don't remember if we talked about this or not, but you can, by suitable analysis of the structure of these operators, determine what this proportionality constant is, and in this case it's h bar. Likewise, we know S plus acting on the up state isn't going to give us anything. We can't raise the up state any higher than it already is. This gives us 0. Similarly, S minus acting on the up state lowers down to the down state with the same proportionality constant, h bar, and S minus acting on the down state, we can't lower it any more than it already is, gives us 0. As before, you can write out matrix equations here. So say S plus. Suppose I write S plus as this unknown 2 by 2 matrix A, B, C, D. Acting on down, which is 0, 1, we get h bar times up, 1, 0. You're going to get two equations from this. You're going to get another two equations by knowing that S plus acting on up is 0, but I'll skip the details here. You can solve the system of equations that results here very easily, and what you find is that S plus, expressed in this basis, is given by h bar times 0, 1, 0, 0. The only non-zero component is the upper right. Likewise, expressing S minus as some unknown matrix, plugging in the definitions of the up and down kets expressed in this basis of up and down kets, you get a system of equations that you can very easily solve to find that S minus, expressed in this basis, is h bar times 0, 0, 1, 0. The only non-zero component is the lower right. You can start to get a feel already for the degree of symmetry that we're going to have when we're talking about the spin 1/2 system. Upper right, lower left. Diagonal identity, diagonal 1 and minus 1 for S sub z, for instance. These 2 by 2 matrices have a very nice, very symmetrical sort of structure. Now, knowing what S plus and S minus are, we can figure out what S sub x and S sub y are. Basically, if you remember, S plus was defined, the raising operator was defined in terms of the x and y component angular momentum operators. Likewise, S minus is given by Sx minus I Sy. These were our definitions, and these definitions carried over from the orbital angular momentum case, back when we were talking about a more general case, and we wrote L plus is equal to Lx plus I Ly. Same expression, I'm just using S instead of L, since I'm talking about a different form of angular momentum. Now you can treat these two equations naturally as a system of two equations and two unknowns that you can use to find Sx in terms of S plus and S minus, or Sy in terms of S plus and S minus, or you can simply look at the equations. If I told you that S sub x was equal to S plus S minus divided by 2, it shouldn't surprise you. If I add these two equations together, Sx plus Isy plus Sx minus Isy, the Isy parts are going to cancel out, and I'm going to be left with 2Sx. So I divide the overall result by 2, and I get Sx. Similarly, Sy, same sort of superposition, S plus minus S minus over 2I. S plus minus S minus is going to be Sx plus Isy minus Sx plus Isy. So my Isys combine, and I get 2 Isy, which I want to cancel out the 2I to get just Sy. So these are our operators. And now, knowing the matrix definitions of S plus and S minus from the previous slide, you can simply plug and chug. Sx, expressed in this basis, is h bar over 2, 0, 1, 1, 0. Sy, expressed in this basis, is h bar over 2, 0, minus I, 0. So these are our Sx and Sy. And now we know all of the operators. We have an expression for S squared, an expression for Sz, an expression for Sx, an expression for Sy, and of course, coming along for the ride, we have these S plus or minuses. These matrices go by a different name. They're called the Pauli spin matrices, for the most part. And I really struggle with the notation in an equation like this, because S is a vector, but I don't know whether to give it a hat, to call it an operator, to boldface it to give it an operator, or to put a vector arrow on top of it since it's a vector operator. So I'm just going to leave this as is. Context is usually enough to figure out what's an operator and what's not an operator, but you really have to keep in the back of your mind that sometimes these things are going to be confusing. So be very careful with the notation. Try to be as neat as possible with how you write these things down. It's very easy for a sigma to become an S, or a 2 to disappear, or a minus sign to become a plus sign, or an I to disappear. Keeping track of all of this requires a great deal of attention to detail, which is not something I'm very good at. I'll openly admit that. But while notationally speaking, this is a rather complicated expression, all we've really done is pull the h bar over 2 out of our expressions for the S sub x, S sub y, and S sub z operators, defining them as lowercase sigma sub x, sigma sub y, and sigma sub z operators, or matrices in this case, since we're working in the basis of the up and down S sub z eigenstates. So these are our Pauli spin matrices. The x component, for instance, S sub x, just to close the loop a little bit, is going to be h bar over 2 sigma sub x. Likewise, S sub y and S sub z, expressed in terms of these sigma sub x, sigma sub y, and sigma sub z. What's nice about this is it's relatively easy to manipulate. Like I said, this is about as easy as the math in quantum mechanics ever gets. The eigenstates of S sub x. Suppose we want to find the eigenstates of S sub x. That's a reasonable question. What does this state that has a definite value of the x component of the angular momentum actually look like? What we want under those circumstances is the eigenstate of S sub x. We want to know what the eigenvalues are. We want to know what the eigenstates are. Now we're working in this up-down basis. We have an expression for S sub x in this up-down basis. So h bar over 2, 0, 1, 1, 0, that was our expression. This is our sigma sub x. And our unknown vector, let's just call it xy. We don't know what the eigenstate is. We don't know what its components in this up-down basis are. Is equal to lambda x, y. This is a 2 by 2 matrix eigenvalue problem. If you don't remember how to solve 2 by 2 matrix eigenvalue problems, I suggest you refer to the appendix in the book on linear algebra, or go back to our lectures where we did a very brief and unfortunately crappy review of linear algebra. I made those lectures at about 1 in the morning and I was running out of gas. The eigenvalue problem, just to review, you solve this system. Essentially, this only has a non-trivial solution if the determinant of this matrix, the net matrix here, moving this lambda times xy to the left-hand side of the equation, the determinant of that matrix has to be equal to 0 in order for it to have a non-trivial solution. So we want the determinant of the matrix, and I'll write it expanding the h bar over 2 into the matrix and subtracting the right-hand side off of this. We're going to have minus lambda h bar over 2, and then h bar over 2 and minus lambda for our diagonal components. We want the determinant of this matrix to be equal to 0, and that gives us our characteristic polynomial. The polynomial you get from the determinant of this matrix is very simple. Minus lambda times minus lambda minus h bar over 2 times h bar over 2. So we get lambda squared minus h bar squared over 4 is equal to 0. This is very easy to solve for lambda. We get lambda equals plus or minus h bar over 2. So those are our eigenvalues. This should not be terribly surprising. We chose the z component of the angular momentum more or less capriciously, so we should end up with the same sort of behavior if we had chosen the x component of the angular momentum. These eigenvalues now are the results that we would get for observations of a real physical quantity, the angular momentum, the x component of an angular momentum. So they can't really depend on the way we do the math. These are real sorts of physical things. So the fact that we get the same sort of results for the x component as we did for the z component shouldn't surprise you. Our x eigenvalues, or the eigenvalues for the x angular momentum operator, are plus or minus h bar over 2. Finding the eigenvectors associated with this is a matter of going back to the original equation, substituting in lambda, and solving the system of equations that results. I'm going to go back to this expression, which essentially this matrix multiplied by xy equals 0. That's the easiest way to get at these things. And if I substitute in plus or minus h bar over 2 into this sort of structure, plus or minus h bar over 2, h bar over 2, h bar over 2, plus or minus h bar over 2. Oh, sorry, I shouldn't be writing plus or minus. I should be writing minus or plus. The plus sign here, the top sign, going with the plus eigenvalue, since we end up with a minus sign here going back into this matrix, means we're going to have the opposite, minus plus instead of plus minus. So this matrix, multiplied by xy, equals 0, 0. This is equivalent to our original system if we substitute in the eigenvalue, either plus or minus h bar over 2. Solving this system of equations, or just doing the matrix vector product, means we end up with minus or plus h bar over 2x plus h bar over 2 y is equal to 0, or h bar over 2x plus, minus or plus h bar over 2 y is equal to 0. Both of these equations, I can divide out the h bar over 2, both of these equations equivalently tell me that x is equal to plus or minus y. So this didn't actually solve to tell me what the eigenvectors are, but that's what you expect from an eigenvalue sort of system. The system of equations you're going to get here will always be singular, because we generated that system of equations by enforcing it to be singular, saying the determinant has to be equal to 0. So you have to use a little bit of intuition and cleverness to figure out what the solution is actually going to look like. X is plus or minus y, so I could write, for instance, that the eigenstate associated with the plus h bar over 2 eigenvalue is coming, again, with the plus sign now, is x equals y, or just something like 1, 1. That works, but that's not normalized. Let's run with that, actually. Let's say we substitute in x equals 1 and y equals 1. This is now for our h bar over 2 eigenvalue. When we normalize this, you're going to divide by the sum of the squares of both components, i.e. 2. We're going to divide by square root of 2. Our actual normalized eigenvector is going to be 1 over root 2, 1 over root 2. These 1 over root 2's are things that you see a lot when you're dealing with two-state quantum systems. And this guy, Griffiths calls this chi plus with a superscript x to signify that it is the eigenvector associated with the x component of the spin angular momentum with the plus sign in the eigenvalue. If we're working with the minus h bar over 2 eigenvalue, we're going to get the opposite signs here. So if I said 1 minus 1, well, I'm going to get something very similar when I normalize it. 1 over root 2 minus 1 over root 2. And Griffiths calls this chi minus with the superscript x. So these are our eigenvalues and eigenvectors for s sub x. What that means is that these are the states with definite x component of angular momentum. So this is a little bit strange. If I combine two states with definite z angular momentum in this very specific superposition, I end up with a state of definite x angular momentum. And depending on the sign of the superposition here, whether I add them together or subtract them from each other, the plus z component or the minus z component, the spin up case or the spin down case, if I say spin up plus spin down, I get plus spin in the x direction. If I say spin up minus spin down, I get minus spin in the x direction. It's a very strange sort of thing, but this is the fundamental weirdness of quantum mechanics. That's just how these things actually work in the real world. For instance, sequential measurements is the sort of thing that we can explain and understand reasonably easily from the perspective of the mathematics in the spin 1/2 case. Suppose I have some wave function, some state, and I don't know anything about the angular momentum associated with this, the spin angular momentum now. If I measure the z component of the angular momentum, you know what I'm going to get as a result of that. There are only two possible outcomes for a measurement of the z angular momentum. I could get h bar over 2 or minus h bar over 2. Suppose I get minus h bar over 2. If I take this state and I go to, say, measure the x component of the angular momentum now, I've measured s sub z and I've gotten minus h bar over 2. Back when we were talking about the generalized statistical interpretation of quantum mechanics, you know that after a measurement that gave you a particular eigenvalue of the Hermitian operator associated with the observable that you're measuring, the quantum state now is, the quantum system now is in the state with the eigenvalue associated with that measurement. Essentially, the wave function collapsed. And since we're talking about a two-state wave function here, it's not necessarily a collapse of a wave function, but whereas what was originally potentially a superposition of up and down spins, we now know is in the down state. So we have the down state now, and we want to measure s sub x. We've prepared a quantum system in the down state. What are the possible outcomes for a measurement of s sub x? Well, the s sub x measurement could be, in principle, either h bar over 2 or minus h bar over 2. These are the possible outcomes, and we don't know necessarily which one is more likely yet. In order to figure out which one is more likely, you have to express this state, the ingoing state, as a superposition of the plus and minus eigenstates of s sub x. So the algebra problem we have to do to understand the outcomes of this second measurement is to express minus as a superposition of something times what Griffiths called chi plus x and chi minus x. In the algebraic notation, working in the basis of spin up and spin down, we know what the spin down state is. Very simple. 0, 1. we know what the eigenstates of the spin or S sub x operator are. We have 1 over root 2, 1 over root 2 for one of them, and 1 over root 2 minus 1 over root 2 for the other one. We're going to be combining these things together, and we want to make it equal here. What are these multipliers going to be? Well, you can see right away that if I add these two together, I can potentially get this term to cancel out. I don't want it to cancel out, so I'm going to have to be combining these things with a minus sign. If I multiply this one by 2 and this one by 1, if the numbers that I'm multiplying these guys by, they're what I'm going to replace the question marks with in this expression, if those things were unequal, I wouldn't get the top ones to completely nullify. The only remaining thing is that I need to normalize these things. And as before, what you should expect to see when you do normalizations like this is 1 over root 2's appearing. The 1 over root 2 in the probability context is going to get squared and become a half. So essentially this means that I have, if I prepare a quantum state in this system, or a quantum system in this state, I can treat it as an equal superposition of these two states, and an equal superposition properly normalized in the sense that I have to have something like down inner product with down equals 1, or writing this out, I have to have row vector 0, 1 complex conjugate multiplied by column vector 0, 1 not complex conjugated. I have to have that equal to 1. That's okay. If I did that in terms of these states, you would find out that it actually works as well. So make sure everything's normalized, but keep in mind that we're only ever working with two states here, so we're only ever going to be superposing two things together. The superpositions don't have to be equal, of course, but I feel like I'm starting to ramble here, so I'm going to go back to the original problem and move on. We had a quantum state in an unknown system, measured the z component of the angular momentum, supposed that we got the minus h bar over 2 angular momentum eigenvalue, which meant that our quantum system was in the down z component of angular momentum eigenstate. And then in order to figure out the outcomes of a measurement of the x component of the angular momentum, we expressed that down quantum state as a superposition of eigenstates of the S sub x operator. This superposition then tells us that actually the down state is an equal superposition of the plus h bar over 2 and the minus h bar over 2 eigenstates associated with the S sub x operator. So actually, both of these are equally likely. This one is going to have a probability of 0.5. This one's going to have a probability of 0.5. So that's all well and good. It tells us what the outcomes of these measurements are. And this is something that hopefully doesn't surprise you too much, but should really have surprised you a lot when you first started to study quantum mechanics. I have a state, an unknown state. I measure the z component of the angular momentum. I determine it to be minus h bar over 2. Then I measure the x component of the angular momentum. And I find that it is going to be either h bar over 2 or minus h bar over 2. Knowing the angular momentum in the z direction didn't provide any information about the angular momentum in the x direction. What's really surprising about all of this is if I got this guy, if I observe minus h bar over 2, then I know the outcome of the measurement has essentially collapsed the wave function again, and it's collapsed it down into this state. So I know I'm working now with something that's 1 over root 2 minus 1 over root 2. This is my new quantum state. If I went back to measure S sub z again, I would have to re-express this as a superposition of up and down in order to find out what those outcomes would be. And you can probably see, given that up is just 1 here and 0 here, that I would have to write this guy as 1 over root 2 up minus 1 over root 2 down. Which tells me that we have an equal superposition of up and down, which means if we measure S sub z again, we would get either h bar over 2 or minus h bar over 2 with equal probability. So if we know nothing about our state, measure its z component to be down, then measure its x component to be negative, and then measure its z component again, we've forgotten about what the z component was. The measurement of x perturbed the system to the extent that we no longer had any information about the z component of the angular momentum. Mathematically speaking, this all boils down to manipulation of row and column vectors with only 2 components and 2x2 matrices. And 2x2 matrices are about as easy to work with as matrices ever get. So the spin 1/2 system is a very common test case for quantum mechanical systems. To check your understanding, I found the eigenvalues and eigenvectors of S sub x. I'd like you to go ahead and find the eigenvalues and eigenvectors of S sub y. And you can do that however you want. You can use Wolfram Alpha, you can use Sage, you can use Mathematica, use whatever you want. And then on the basis of knowing those eigenvalues and eigenvectors, suppose I prepare an eigenstate of the x component of spin angular momentum and measure S sub y. What are the possible outcomes and their probabilities? Or, likewise, if I measure S sub z, what are the possible outcomes and their probabilities? Given the definition that we gave in the last lecture of spin as essentially an angular momentum operator algebra that doesn't actually have an obvious counterpart of particle motion, let's take a look at the operator algebra and the associated states, their eigenvalues, their eigenstates, etc., of the most basic case, the most basic non-trivial case, spin 1/2. Spin 1/2 is the system that you should think of if the quantum mechanical system you actually are trying to understand is too complicated. Spin 1/2 is about as simple as quantum mechanical systems get, while the basis of spin up and spin down are chi plus vector, which I'm also writing as just up, is given by simply 1, 0. Likewise, chi minus, or spin down, is given by 0, 1. If these are the vectors that we're working with, what are the operators that we're working with? Our operators are going to be things that act on these two component vectors, so they're going to be 2x2 matrices. For instance, let's consider S squared. We know what S squared does from our consistency. And what that means is that we're working with S is a half and M is either plus a half or minus a half. Another very common notation, and one that I'm going to use in this lecture, is to call the plus case up arrow and the minus case down arrow. So spin up and spin down. What's nice about this, the fact that we're working with a two-state system, is that no matter what our operator is, it's going to have a representation as a 2x2 matrix. The vectors that we're working with then, this chi plus, expressed in this basis, still having rich behavior. So essentially what we're working with is S, which was our spin angular momentum counterpart for the L quantum number in orbital angular momentum of 1/2, which means we have an M counterpart in the spin angular momentum of either minus 1/2 or plus 1/2. So that's the structure of our system. We're working with two states. So S is a half, and our allowed values of M are then minus a half and plus a half. The two states that we're working with then, I'm going to call them chi plus and chi minus, iteration of the operator algebra. S squared, which is our counterpart for L squared, S squared, acting on the spin up case, is going to give us our eigenvalue, which was h bar squared S plus 1, and this is an eigenstate of S squared by construction. S, in this case, is 1/2, and if you plug this in, you find out this is equal to 3/4 h bar squared. We can use this sort of expression, which of course has